Hey guys. Okay, so today what we're going to be doing is we are going to be looking at why does a rainbow have colors? What causes that? Why can you see all of the colors of the visible spectrum, right? The red, orange, yellow, green, blue, violet, sometimes pink, depending on how close the top red is, right? Why can you see those colors in a rainbow? All right, and through that, we're going to be looking at these objectives here. There's a lot of them. I'm so sorry for all of your writing, but you're going to be able to describe the process that creates atomic spectra. You're going to be able to describe relative energies, wavelengths, frequencies of ultraviolet, so UV, visible, infrared, which is IR, microwave, X-ray, and radio waves. You're going to be able to distinguish between absorption and emission of energy. And you can determine wavelength, type of energy, and color of visible light if applicable, right, given your electron transition. All right, so let's start today. We're going to review a little bit about the Bohr model, and we're going to get into it, right? So we have been learning in the past couple days, right, what a Bohr model is. And we know that we have a nucleus, okay, filled with protons and neutrons, and surrounding the nucleus we have electrons, okay? And electrons circle the nucleus in certain fixed energy levels, or shells, what we call them, right? And we were looking, right, if I have something closest to the nucleus, it's energy level 1, then energy level 2, energy level 3, and so on, right? And those areas surrounding my nucleus is what I'm going to call orbitals, right? So regions of space that surround the nucleus where there's a 95% probability of finding an electron, right? So if I were to pick any one spot surrounding my nucleus, there's a 95% chance that I could find an electron. All right. And when we were looking at the Bohr model, right, Niels Bohr is the one who created it. Okay. Electrons exist in energy levels and defined orbits around the nucleus. Sorry, guys, I'm still losing my voice a little bit, so it's a little wonky, okay? But electrons exist in energy levels, right? We saw that the other day, right? Energy level 1, energy level 2, energy level 3, etc., right? And they have defined orbits, meaning that if I have an electron that's in the n equals 1, it's going to be found there. Right? N equals 2, it's gonna be found there, okay? And each orbit corresponds to a different energy level, right? Electrons cannot be found between energy levels. So I'm not gonna find an electron here, or I'm not gonna find an electron here. They're gonna be in their energy level, right? They are not gonna be found in between, okay? Think about it as rungs on a ladder, right? When you're climbing a ladder, you can't really have your foot in between a rung and be stable, right? You're gonna fall, or your foot's gonna drop to the next to the next rung. Okay, that's the exact same thing with electrons. Okay, and the further out you go from the nucleus, the further out you go in your orbit, the higher your energy level will be. Meaning your lowest is obviously 1. It's closest to the nucleus, so I'm not gonna have that much energy. More energy, more energy. Okay, so as you go out, the higher your energy level. This helps us start to look at what we call the quantum mechanical model, okay? And that is a current model that we look at for the atom that looks at light as acting as a wave and a particle, okay? And light has to do with electrons, all right? And so we have a wave-particle duality of an electron that will give us light. So when we talk about the wave-particle duality, we have to talk about the wave nature, okay? And two properties that we look at is frequency and wavelength, all right? So if I look here, we see what a wave will look like, okay? A frequency is how many waves happen per second, right? So if from this point here to this point here was 1 second, I would have 1, 2 total waves. So my frequency would be 2 waves per second. If this to this was 1 second, I would have 1 wave per second, okay? The wavelength is the difference between, or the distance between two corresponding points, right? Meaning if I took the top part of each wave, that's a wavelength, bottom part, that's a wavelength. So it's from, if I have the tops right? This to this is 1, right? Another wavelength would be if I had another top part over here, it would be the difference from this to this, right? So that's my wavelength, okay? And when we look at the wave nature of light, we see that frequency is inversely proportional to wavelength, meaning, right, if my wavelength increases, meaning my space between my waves increase, my frequency actually decreases, right? So say from here to here, right, is 1 second. Okay, so up here and then this guy right here is 1 second. You see that I have a greater wavelength, but I only had 1 wave per that second. If I come down here though, right, my wavelength decreases, right? My space is smaller. And I have 1, 2, 3, 4 waves that have gone by per second, right? So you need to keep in mind that as wavelength increases, frequency decreases. If wavelength decreases, frequency increases, right? So they're opposite of each other. They're inversely proportional. That's what that means. All right. The next part we have is the particle nature of light, okay? And we have a couple things that we talk about with the particle nature. These are electrons. These are our actual particles, right? We have one thing called the photoelectric effect, meaning when light strikes a metal, electrons are ejected. Okay, that's what my photoelectric effect is called. And we're going to look at that a little bit later in this unit once my stuff from Amazon gets in, because you guys know how much I love my Amazon Prime. The next thing we have is what's called an atomic line spectra, and that means that hydrogen gas is emitted, okay, or hydrogen gas emits specific bands of light, okay, right? So depending on how an electron is moved, okay, there's certain energies that will give you light in the infrared, visible, or ultraviolet spectrums for a hydrogen atom. And we kind of see that here, right? If I have an electron that moves from 7 to 1, I'm going to be in that ultraviolet. If I have something that moves from, let's see, 6 to 2 to 3, yeah, that's 3. 6 to 3, I'm going to be in infrared. Okay, visible light's up here. Okay, something I want you guys to keep in mind. If an electron moves from any energy level down to 1, it's going to be in ultraviolet. If anything moves from a energy level down to 3, it's infrared. Down to 2 tends to be our visible light. Okay, so that's my atomic line spectrum, meaning that depending on how my electron moves, I'm going to be giving off different types of light. All right. So let's go back to the photoelectric spectrum and the photoelectric effects, right? We know based on the wave duality or wave particle duality that there is a minimum frequency now that's needed to eject an electron, okay? And that's going to change my location. And we only can explain this by energy packets of light called quantum. Okay, quantum is the minimum amount of energy that can be gained or lost by an atom, and specifically an electron. And when we give off light, okay, these energy packets of light, that's what we call photons, which are massless particles of light of a certain quantum of energy. And this is based on the frequency and wavelength of a photon, okay? And we're going to wrap all of this together so you'll see exactly what all of this means, okay? The last thing before we get into the practice part is the Heisenberg uncertainty principle, right? Remember that the Bohr model tells us that electrons exist in energy levels and defined orbits around the nucleus, right? However, Heisenberg tells us that one cannot know both position and energy of an electron at the same time. So we can either know the location, right? If it's in energy level 1, energy level 2, energy level 3, or we can know if it's exerting energy, meaning it's going to be changing energy levels based on my photoelectric effect, based on that photon quantum that we've been talking about. So I can't know both where the energy is or the location, okay? So let's look at this a little bit deeper when we talk about location and energy, right? When my electron is in the lowest possible energy state, okay? That is what I call ground state. It's not always n equals 1. I'm actually going to take that out. Okay. But it's the lowest possible energy level of an electron. Okay. I'm going to move that. There we go. Okay. And this is the most stable location for an electron. Okay, so I can show that here, right? It's my most stable, it's my lowest possible energy. It's where they want to be. But when an electron absorbs energy, it's going to travel to a higher energy level, right? So from here up to here, it's absorbing energy, right? It's taking it in. When we take that in, when we travel to that higher level, is what we call an excited state, meaning that the atom, right, has an electron now that has higher potential energy than the ground state. Okay, so I am now at a higher energy level, so I have higher potential energy, and it's different than my ground state. Okay, so I now have more energy. I absorbed a lot of energy. Okay, when my electron then falls back down to ground state, because it doesn't want to be up here, it wants to be stable. When it's dropping back down, that's when light is going to be released. Okay, that photon is going to be released as it drops back down. And when it drops back down, we said, right, that's when light is going to be produced, right? So to sum it all up, when energy is supplied to an atom, my electrons move to an excited state, okay? When they return to their ground state, meaning where they came from, they're going to emit energy by radiating light, okay, giving it off as photons. And different colors of light are emitted based on the energy level change that occurs, right? So the energy level that the electrons starts at and falls from. And when it gives off that light, that's when we call the electromagnetic spectrum. All right. So let's look at an example and then we'll send you off to practice, right? We're going to use two things in your reference table, so make sure we have those handy, right? When we see this here in your reference table, right? The higher the N, the more excited the state will be, or the higher the energy level, right? So more energy for each of these. And when we jump to a higher level, okay, we're going to an excited state, and then it's going to drop back down to its ground state, and it's going to give off light, okay? So let's look how this works, right? If I have an electron fall from n equals 6 to n equals 2, meaning energy level 6 to energy level 2, I want to know the wavelength of light that's going to be emitted, what that means for frequency, and what the region of the spectrum corresponds to that wavelength, okay? How I'm going to do this is I'm going to use this guy right here, and I'm also going to use what is underneath it here, all right? So we have 4 steps, so pause it if you need to and copy these down. But when I do this, I need to first find my higher energy level ring, okay, to find my wavelength. Then I need to find the line that shows this higher energy level dropping to my lower one. Then I find my wavelength associated with that energy change, and I use the Bohr model chart to determine what type of light is given off, right? So if I go back to this guy here, right, I have n equals 6 to n equals 2. So I find where my dot is in my n equals 6, right? So n equals 6 is that greatest one. I see 1, 2 possible options. And I follow the line that goes all the way to n equals 2, right? So n equals 2 is this ring right here. So that must mean that it's this line here, okay? And when I follow that line down, I find out that it's in my visible spectrum, okay? Anytime anything falls in the visible spectrum, we then have to move to this guy here, all right? And how I do that is whatever my wavelength was, okay, for what we found, right? So if I look, let me go here, right? I found was 410. That means my wavelength is 410 nanometers. I'm going to place a decimal point between the first and second digits and find the color, right? So if I have 410, I'm going to put a decimal between 4.10, and I find that it falls in my violet spectrum. All right. So what I want you guys to do is I want you to do these practice problems